All right, so we've gone through the conceptual run through of neural networks, and I've also gone through some of the nitty-gritty, more mathy details. And so for the remainder of this lecture, I'm going to I'm going to show you an actual neural network model, and then I'm going to talk about the characteristics and limitations of neural networks. So first, we're going to talk about a real neural network. This is called the interactive activation model of speech production. So in this model, it's trying to model, so this neural network is trying to model speech production, how well you can produce speech. Okay, so if I show you a picture, let's say, of a cat, right? This neural network makes certain predictions about what kinds of errors you're more likely to say, as well as correct responses that you're likely to say. So it's trying to model speech production as well as so correct speech production as well as errors in speech production. So it's also called a parallel distributed processing model with and it has layers that correspond to semantic features, words, as well as phonemes or the constituent sounds, the sounds that make up the words. Okay. And all connections are bidirectional. That means um, that activation can spread from the semantic to the words, but it can also spread back, get sent back to the semantics. And, although the word dog sends its activation to the phonemes, let's say duh, and g, the the reason it's bidirectional is because the phoneme layer can send its activation back up to the word layer. Okay. And I'm going to go through this in a bit. I know it probably doesn't make sense right now, but I'll show you with an animation. So yeah, activation spreads through the network and in a bidirectional fashion. So activation can spread up or down. And the word node that receives the highest activation gets selected or retrieved. And then the phonemes that receive the highest activation are selected, right? So they get retrieved. And then you say the word, right? So if I showed you a picture of a cat, right? Maybe these three semantic nodes might get activated. They might spread their activation to cat, but also to rat and dog, let's say. And then the activation would spread down to the constituent phonemes or sounds. And then the phonemes would send their activation back up. And then then the words would send their activation back down to the phonemes, right? And so that's why it's called bidirectional. Okay, here's an example. So imagine if we have like these semantic units or characteristics or attributes. So if I showed you a picture, if I showed the neural network a picture of a cat, right? Well, then this unit, furry, the semantic unit that corresponds to furry, the semantic unit that corresponds to whiskers, and the semantic unit that corresponds to the idea of purring, purrs, they're all going to get activated. Okay. And notice how rats and dogs have whiskers and are furry as well, right? So the activation is going to spread to related concepts. And that's precisely what we find is that, or what we would expect, right? So that furry and whiskers would send their activation to cat, but also dog and rat, whereas purrs would send only its activation to cat, and so cat would be activated the most. So makes this makes this prediction that if we stopped here, right, cat would be the one that would get selected. But it doesn't stop it there right away. So then cat is the most active, followed by rat and dog. Well, then they send their activation to the phoneme layer, right? And so notice how r, duh. So like, okay, dog is duh, ah, and g phonemes, and those get activated because the dog node got activated. And so it's going to send its activation to d, ah, and g. And then rat, for example, is going to send its activation to r, ah, and t. whereas cat is going to send its activation to k, a, and t. So notice how a and t get the most activation. Out of all the phonemes, a and t both get the most activation. And then here's the kicker. So the cool thing about this, right? The reason it's called a an interactive activation model is because the phoneme layer can spread its activation or send its activation back up to the word node. So in this case, at and to were the most activated. So they're going to send their activation to cat and rat the most. Dog's going to get a little bit of activation. Matt will also get a little activation. Fog is also going to get a tiny bit of activation. But notice how cat has the most activation, followed by rat, and then followed by dog, right? And so then rat and cat are going to, so all the words are then going to send all their activation back to their constituent phonemes, right? And so it makes this prediction that if you were to say, see a picture of a cat, or if so, the neural network makes a prediction, right? If you show a picture of cat to the neural network, it's more likely, it's going to say cat often, right? But likely to say, it's more likely to say rat than it is dog. So if the neural network makes an error, a speech error, so to speak, then it's more likely to say rat than dog, and that's simply because rat and cat share phonemes. They have phonemes in common, and because phonemes can determine or have an influence on what words actually get selected, as a result, you're more likely to say rat than dog, right? So just to recap here, the semantics of cat turns on the word node corresponding to cat. And then it also gives some activation to related words or related concepts, I should say, such as dog and rat. And then the word cat turns on the corresponding phonological nodes, such as ka, a, and t. But then the phonological nodes feed back activation to the word layer, strengthening cat and turning on rat as well as mat. Okay. And so cat, in this example, cat should be most active, followed by rat. And that's because, right, the word node, which word you select, is influenced by the activation from the semantic units, but also from the phonological units or the sound-based units. And so, if the mind is like, if we're trying to model how the mind works, right, by using a neural network such as this, well, this makes a very specific prediction, which is that in cases where you make it, so if I showed participants a picture of a cat, they're they're likely to say cat. They're most likely to say cat, right? They're most likely to get the picture naming task right. However, on cases in which they get it wrong, let's say if it's a speeded task where they have to say it as fast as possible, they're more likely to say rat than dog. In other words, they're more likely to make mixed errors, errors that reflect both semantics and phonemes. Okay. Okay. And then in the next video, we'll talk about some of the characteristics and limitations of neural networks.